A block attached to a rotating rod. A 4 kg block is attached to a vertical rod by means of two strings. When the system rotates about the axis of the rod, the strings are extended as shown in figure, and the tension in the upper string, this string, is 80 newtons. Part A, what is the tension in the lower cord? Part B, how many revolutions per minute does the system make? Part C, find the number of revolutions per minute at which the lower cord just goes slack. Part D, explain what happens if the number of revolutions per minute is less than that in part C. Okay, so what we need to do is first draw a free body diagram of this block, so we can identify the forces acting on the block as the tension in the upper string, tension in the lower string, and the weight of the block. Alright, so free body diagram. So in part A, we have a free body diagram for the block. The block is modeled as a particle. It feels the weight mg, and this is my vertical axis. There's a tension in the lower string and there's a tension in the upper string. So we have T up, T down, and as you can see from the figure, these will make an angle alpha with respect to the vertical axis here. So this is alpha. Okay, now this is our y-axis, the vertical axis, and this is a rotation, so we have the rotation of this block around this central axis, so we have to draw a radial axis here. This is radially outward direction. Okay, and the net force on the y-axis should be 0 because the block is moving on a plane here. It's not moving up or down. Therefore, we should have T upper chord cosine alpha acting in j-hat direction is equal to T lower chord, T down, cosine alpha plus mg. So this force is acting in minus j-hat direction. So you can see that the tension in the lower chord will be equal to the tension in the upper chord cosine alpha minus the weight mg divided by cosine alpha. So this will be equal to tension in the upper chord minus mg over cosine alpha. So we can calculate now the tension in the lower chord. Tension in the upper chord was given as 80 newtons. This is a 4 kg block. So we have 4 times 9.8 divided by cosine alpha. Now I have to find what cosine alpha is. This is 2 meters. This is an isosceles triangle here. So you can see that cosine alpha will be this side divided by the hypotenuse. So it will be 1 over 1.25. So I can read it from this triangle here, 1 over 1.25. So this gives us 80 minus 49, which is 31.0 newtons. Okay, so we have calculated tension in the lower chord. Now part B asks me how many revolutions per minute does the system make. Okay, so to answer part B, I have to look at the free body diagram, the radial axis. What is the net radial force acting on this block? Well, as you can see, the tension in the upper chord and tension in the lower chord will have a component on the radial axis in minus r hat direction. So minus t up sine alpha minus t down sine alpha is equal to minus mv square over r, where r is the radius of the circle that we will be drawing on this plane. Okay, so the minus signs will disappear. This will give me tension in the upper chord. Sine alpha, as you can see from this triangle, is r divided by 1.25, so it's r divided by 1.25. The tension in the lower chord times r divided by 1.25. This is equal to mv square over r, centripetal force. Okay, so if I take this into r over 1.25 parentheses and multiply it by r and divide it by m, so I'm going to get r square over, so I'm trying to isolate v here, r square over 1.25 times tension in the upper chord plus the tension in the lower chord, and then I have to divide it by m to obtain v square, and v, remember, is 2 pi r over the period, or 2 pi r times the frequency. So here I can substitute 2 pi r frequency square for v, so this will give me 4 pi square r square f square. Okay, so I have r square on both sides, so these r squares will cancel. So I can see that the frequency of rotation will be given by tension in the upper chord plus tension in the lower chord divided by 4 times 1.25, 5 m pi square square root. Okay, so if I substitute the numbers here, tension in the upper chord is 80 newtons, in the lower chord is 31 newtons, divided by 5 times 4 kilograms times pi square square root. This gives us 0.750 Hertz for the frequency. Now I want to know how many revolutions per minute I have. So this is in revolutions. Remember that Hertz means number of revolutions per second, but I want to know how many number of revolutions per minute I have. So frequency of 0.750 revolutions per second is going to be 0.750. We have in 1 minute 60 seconds, so 60 revolutions per minute. So this will be 45.0 RPM, or revolutions per minute. Okay, Now part C asks me, find the number of revolutions per minute at which the lower cord just goes slack. Alright, so part C. So what does it mean? The lower cord goes slack. Well, this implies that I have a tension in the lower cord 0 newtons. Alright, so it's this critical value of frequency. So the net force on the radial axis from my free body diagram will become, now because the tension in the lower cord is 0, just this part, minus T up sine alpha, and this must be equal to minus mv square over r. So you can see that tension in the upper cord times sine alpha is r divided by 1.25 is equal to m v square 4 pi square f square r square divided by r, mv square over r, and we have this r cancelling with this r and also this r, so we have no r's left. And therefore, the frequency becomes tension in the upper cord divided by 5m pi squared square root. This will give me in hertz, so I have to multiply this by 60 to get it in RPM. Now, on the other hand, if I go back to the free body diagram here, when the tension in the lower cord is 0, this tension in the upper cord will change because I have the same equilibrium condition on the y-axis. So if I write the net force on the y-axis equals to 0, I see that T up cosine alpha must be equal to mg. So this also affects this equation because this part becomes 0, and therefore I find that the tension in the upper cord will now become mg divided by cosine alpha, which is 4 times 9.8 meters per second square, 4 kilograms times 9.8 meter per second square. Cosine alpha was 1 over 1.25. From this triangle here, it is 1 over 1.25. So this becomes 49.0 newtons. So we can substitute this new tension in the upper cord, 49 divided by 5 times 4 times pi square square root, and this has to be multiplied by 60 to convert to RPM. So this gives us 29.9 revolutions per minute. Okay, and part D. Explain what happens if the number of revolutions per minute is less than that in part C. Okay, so we have a frequency f is less than 29.9 RPM. Now when I look at the net radial force, which is mv square over r, or it's also equal to m 4 pi square f square r square over r. The r's cancel, which is 4 pi square f square mr. So decreasing the frequency, we will be basically decreasing this radial force. This decreases, and Basically, because the tension is related to tension component is basically giving me the centripetal force here. So I will find that the tension in the upper cord decreases, and what happens is, if the tension decreases, T up cosine alpha will become less than mg. So this will affect my equilibrium on the y-axis. So this will become less than mg. So what will happen is that the block falls to a level such that alpha decreases to alpha prime to maintain the equilibrium on the y-axis. T up cosine alpha prime will be equal to mg. So we will see that the block will start going down. As you decrease the frequency, the block will be approaching the central rod. The alpha will decrease so that we will have the reduced tension now becoming being able to maintain this equation on the y-axis, so that we will have a new equilibrium condition established. All right. So to summarize, we have a block that is attached to a vertical rod by two strings, and this rod is rotating and there is a tension in the upper cord of 80 newtons. The length of the cords are 1.25 each, with 2 meter distance between the support points. So first we need to calculate the tension in the lower cord, the frequency of rotation in revolutions per minute, and the condition for which the tension in the lower cord becomes zero when we change the frequency, and what happens if the frequency is even less than this critical value. So that was the question. So first we identified the free body diagram of the block, identified the forces, tension in the upper cord, tension in the lower cord, mg. And then I was careful about the coordinate system that I need to use for this. There is the y-axis, vertical axis, and there is a radial axis because this is a rotation. This is the radially upward direction. The equilibrium on the y-axis gives me T up cosine alpha is T down cosine alpha plus mg, where cosine alpha can be read from this triangle as 1 divided by 1.25. So these two should be equal. And with that, I can calculate the tension in the lower cord, 31 newtons. If I write the net force on the radial axis, I can find the force responsible for centripetal acceleration v square over r. And this has a contribution from T up and T down components on the radial axis, where sine alpha is now r, the radial distance from the center, divided by the hypotenuse 1.25, and the for uniform circular motion, so I have to note that this is uniform circular motion, I have v is equal to 2 pi r divided by the period, or 2 pi r multiplied by the frequency f. So this t is not the tension, it's the period t, right? And f is frequency. So you can see that if you write v is equal to 2 pi rf, we can isolate f here and find f in terms of the tension in the upper and lower cords divided by the 5m pi squared square root. So this gives us 0.775 Hertz, which has to be converted to revolutions per minute. If you have 0.75 revolutions in 1 second, you multiply it by 60 because we have 60 seconds in 1 minute, we obtain 45 RPM. If the lower cord goes slack, the tension in the lower cord becomes zero. So first of all, this affects the equilibrium condition on the y-axis. So this part is zero. T up cosine alpha becomes equal to mg, and we can calculate the new tension. The radial force is now only minus T up sine alpha, which is equal to the centripetal force, minus mv square over r. And we can calculate the frequency in terms of this new upper cord tension, and we find this by multiplying it with 60 as we did in part B as 29.9 RPM. So if I decrease the frequency beyond 29.9 RPM, the centripetal force is decreasing, and that means that the tension in the upper cord will decrease, and T up cosine alpha will become less than mg, which means this equilibrium is now destroyed, so the angle will start closing and this block will start approaching the central rod, and it will fall to a new level, making a new angle alpha prime to maintain the equilibrium condition on the y-axis.